Hi, my name is Bernard Brault, and I want to talk about the coronavirus, but more specifically about the importance of social distancing. A lot of people think that it may not be very important. I want to share with you why it is. So what I have here is there is a infection model. The most basic one, I think, is called the SIR model, and that's what I'm showing here. I've put together the equations here just to show you what it looks like. It's basically three buckets. So you divide the population into three buckets. So the general population, all of us, who were initially susceptible to get the virus, so that's the susceptible bucket. And there is another bucket, which is the ones are infected by the virus. So you go from being susceptible to possibly being infected. Once you're infected, two things can happen. Either you're going to recover or you're going to die from it. So hopefully you're all going to recover, and the recovery rate is pretty good. So the SIR model is very simple. It only has two little parameters you can play around with, and the two parameters are the transmission, how easy it is for the virus to transmit, and then the recovery rate. And it just so happens you may have heard this term, the R0. The R0 is a ratio between these two terms. But since the recovery is pretty high, I'm putting the recovery at 0.99, so really the transmission, which I put here, and it's estimated that the coronavirus transmission R0 is somewhere around between 3 and 4. At least it started between 3 and 4. That's what we estimated. So what I did is I took these differential equations. They're not linear, but they're very simple. You can easily in Excel, solve these things numerically, and that's what I've done here. So I have a time axis. These are, forget about the numbers. They're not 0.1 days. They're not months. They're just a time reference, and this could be anything, and it's not really that relevant for the presentation. There is the susceptible population, right? So we start out as 99.99% of us are susceptible. Nobody has it, so more or less 100%. The number of people who will develop the infection over time, this is this column, and the number of people who've recovered. The plot that you see here is a plot of the number of people infected. I think that's the one that we've all been watching in the news. We hear about the number of new cases and so on, and that's the plot. So, and I think I've used the reasonable numbers, as I mentioned, 3.7. And I want to show you, a lot of people have heard about flattening the curve, and obviously, if the model is right here, and probably is not. Models are never right, just so you know. All right, they're always wrong, but they're still good tools. So if you look at this model, right, the scary part is all of a sudden, we're gonna, like 40% of the population is gonna get this really fairly quickly. And obviously there's no hospital room, no intensive care unit. You've heard Cuomo, you've heard everybody talk about it, need to flatten the curve. So I want to show you what flattening the curve looks like. Right, so it's taking that transmission rate, right, and lowering it. So if I take this, so if you look in 5 time units, whether it's a month or whatever, we're reaching 40% of the population have been infected by this disease, right? So if we reduce the transmission rate, right, from 3.7, let's say, to 2.5, right, take a look at the curve now, and what you'll see is it used to peak at 5 at 40%. Now it's peaking like at after 7 time unit or a little further down, but still 25% of the population. Now 25% is still way too high, right? So we need to flatten up the curve quite a bit more. So if I flatten it up to 1.5, all of a sudden it looks more reasonable, right? It's stretched out and it goes out to 20 or maybe several months, and only 7% of the population will get it. Even though these are big numbers, right? 7%. So I don't think we could all get fit into the emergency room if that were to happen. Now the other thing that's key is that you could go on YouTube and find lots of people that are going to do a better job than I have so far at explaining this with sliders and modeling tools, not Excel. But I want to show you something a bit different than what I've seen in YouTube. So let's go back to the 3.7 here, all right? Because obviously what happened is the transmission rate is not a constant number, it's a variable number, right? So as this disease has evolved, we've changed our habit. We're probably all staying at home, or we're not doing the same thing anymore, right? So obviously the transmission parameter is not a constant, it's something that changes. When did we start changing habits? So let's say you have a state of 10 million people. When we started having somewhere around even less than 1,000 cases, right, which is 0.1% infection, we started changing our behavior. And I want to show you what it looks like. So let's look at the infection rate, right? And I started out with only 0.001% getting it. You have to start somewhere, right? Otherwise, there's no disease. But let's go down to the 0.1%, more or less, after 2 times unit. So right around here, right? So it'd be like right around 2 right there. So we're still in the early stages, but we're, everybody's cases are growing exponentially and so on. And all of a sudden we're supposed to do social distancing. And let's take a look what it looks like. So the 3.7 remains at 3.7. We can't change the past, but here we are, right? So, and that was a couple of weeks ago, and we started doing social distancing. And let's take a look at what it looks like, right? So I'm going to bring this down, let's say, to 2.5. Already the curve starts looking better, but if you look at it around 2.5, you don't really notice any changes in a linear scale. In order to see any changes, you have to go to a log scale. So what I'm going to do is I'm going to make this a log scale, and you'll see what I do. All right. So making it a log scale, you can see here that the exponential growth in a log scale becomes linear. So this is the linear stage. We've done some social distancing now, and as you can see here, we're growing still, but at a different pace, a slower pace. And every day we add a dot here, and we're hoping things are going to get better. But as you can see right there, we're still growing way too fast, right? So obviously, we needed to reduce this transmission rate, not from 3.7 to 2.5 to something much better. So let's assume we got a lot better than 2.5, and it was more like 1.5, right? And let's take a look what it looks like. And now it looks a lot better, right? So here we are, right? And we started social distancing. And here we have about, 0.1%. That's like 1,000 cases out of 10 million. And we're growing. And once we're right around here right now, wondering if this thing is ever going to end. And when you look at the curve, it's not. If it took 2 months to get up to here, this is a disaster in the making, right? So we need to do some more. Either our social distancing was better than this, we're hoping for a break that we don't see, or we need to basically do a lot more than this. So by the time we're reaching this stage, which is pretty much right now, right? So we're like, okay, we need to clamp down. We all need to wear masks, and we need to distance some more. But where are we? We're at 1%, right? So I'm going to go down there to the 1%. So here we are in the time. This time, we're going to improve our social distancing. We're going to start wearing masks. We're going to start doing all kinds of new measures. We're going to force people to stay at at home, and so on. And let's reduce this to 1.2, right? And then go and take a look. Sorry, I wish you could see that chart. As you can see right now, we're seeing a second break in the curve, right? But it's just not good enough. This is 10,000 cases, for months and months and months. So that really is not good enough. What we have to do is reduce that transmission rate. Let's go back to something lower than 1. So let's make it 0.9. Let's say we're really going to do a lot better. So let's go back to that 1.2 and make it 0.9. And let me show you what that looks like. Now it looks a lot better. So we're peaking at 10,000. And rapidly it's not so rapid, but we're going down. And this would be, you'd think, a cause for celebration. And what I want to show you is what would happen if we started celebrating a little too early. So let's say, for example, we start relaxing after we clamp down quite a bit. So let me go down and show you early celebration, what it might look like. So we're seeing quite a reduction, and right there is going back to exactly where we used to be. So reopening for business as usual, back to the 3.7, and what you see right there is a reemergence of the disease, right? So we'd go back to straight to something square like that. Obviously, that's not acceptable, but we need to reopen for business somehow. So what about going back to, something in between? So back to 1.5 and see what it looks like. That's just not good enough. So if it took us 2 months to get to here, right, and we see a reduction, look at that, we're back in trouble. So obviously, one of the things that I never hear in the news is nobody is saying what the R0 is, right? So either we don't know, somebody knows, and they're not telling us. So what I plan to do is, I think I can develop a R0 estimator from existing cases. So that's going to be probably my next video. I hope you enjoyed this, and be safe, keep your social distance, and I think we're in it for quite a bit of time, unless the sun kills this thing, and the model is obviously, as I said, the model is not right. No model's right. All right, take care.